Good afternoon, everyone. I am Donis Marie Ausejo, the partner of Marafi Kila, and we are assigned to report about the grinding metals. So, I will continue to my part, which is the types of grinders used in metal grindings, the surface grinder, bed grinder, and jig grinder. So, surface grinder is an abrasive wheel used to finish the surface of flat surfaces. So, surface grinding is used to produce a smooth finish on flat surfaces. It is a widely used abrasive machining process in which a spinning wheel covered in rough particles or grinding wheel cuts chips of metallic or non-metallic substance from a workpiece, making a face of it flat or smooth. So the parts or the types of the machine are the grinding wheel and wheel guard. Grinding wheels contain abrasive grains and layers of fiberglass bonded into a wheel shaped by another substance. The abrasive grains act as grinding tools, removing material from a workpiece to shape and refine it. Grinding wheels are useful in many grinding and machining operations, while the wheel guard is a specialty synthetic wax developed just for wheels and brake components to protect against brake dust, grime, dirt, mud, water, and more to keep wheels clean and shiny for longer. Next is a splash guard. It is a flap suspended behind a near wheel to prevent tine splash from a muddy windshields of following vehicles. Next is the X-axis hand wheel with power feed. To use the X-axis hand wheel, loosen the X-axis table locks, position the limit stops along the front of the table to restrict table travel and adjust X-axis graduated dial to 0, then use the hand wheel to move the table. While the Y-axis hand wheel with power feed, it moves table back and forth. Increase rigidity of table when Y-axis movement is not required for operation. The next part is the coolant tank. Most CNC machining or surface grinding operations require a topping off of the coolant due to evaporation or the fluid being carried off by chips or parts. Next is a saddle. It is a special surface grinding machine that can process a series of flat surface types. Next is the grinding wheel and the coolant controls, the electrical cabinet, power feed controls, the work table with magnetic chuck, the coolant nozzle, which is nozzles are often used to supply coolant during grinding or machining operations to control workpiece temperature, keep the grinding wheel or tool clean and open for chip flow, enable extreme pressure additives in the coolant to do their job, and flush chips away from the cutting area. Next is the halogen work light, and lastly, the Z-axis hand wheel. So the pit grinder, it is used to sharpen tool pits and milling cutters. The jig grinder is used for grinding complex shapes where accuracy and finish are important. So jig grinder is a machine tool that is used for grinding complex shapes and holes where the highest degrees of accuracy and finish are required. So it is typically uses to removable or air-driven spindle. So next is the different types of metal particles from grinding. So metal particles or the metal dust can be classified based on their size into metal swarf, inhalable dust, respirable dust, and the combustible dust. So respirable dust, it is as the name suggests, is very fine dust that is typically around 1 micron to 0.1 microns. This dust, created by fine metal grinding processes, can pass through the nasal passage into the alveoli of human lungs, where it can cause long-term problems. So these dust particles are so small that they are invisible under normal lighting conditions. So their extremely small size also means that they can breathe deep into your lungs and lead to lung damage. Combustible metal dust. Now, on the face of it, metal does not seem to be combustible. The fact is, fine metal dust, especially of certain metals like aluminum, titanium, and magnesium, can be extremely flammable and can burn at a very high temperature ranging from 2760 degrees Celsius to 4426 degrees Celsius. So, combustible dust is a combustible particulate metal that presents a fine or explosion hazard when suspended in air or the process-specific oxidizing medium over a range of concentrations regardless of particle size or shape. So let's move on to the don'ts. So here are simple but important safety precautions you can find in the form of do's and don'ts that will help prevent workplace injuries while grinding jobs. So here are the don'ts. Don't clean or make any adjustments on a moving grinder. Don't adjust work while the grinding wheel is in motion. Don't force work against a cold wheel. Apply it gradually. Don't over-tighten the grinding wheel retaining nut. Don't use a worn and expired wheel. Don't use a machine with a damaged cord and plug. Don't grind materials for which the grinding wheel is not designed. Don't allow chipping or hacking on the wheel. Don't change the wheel for a larger diameter or a higher speed, peripheral speed higher than the nominal speed. Don't hold the machine in such a way that projectiles can strike you. Don't wear loose clothing, articles, or jewelry while grinding. Don't work on small materials that cannot be secured. Don't bring hand near rotating parts to avoid kickback. Don't use a grinder without a wheel guard. Don't put the grinder on the ground until the wheel has completely stopped rotating. Never use cotton discs for grinding work. Don't use coolant with portable grinders. And don't use an improperly adjusted wheel and only use accessories that are compatible with your grinder. So we must follow all of these to avoid accidents.
Make a plan for touching off in the right spot, and also how to touch off, and how to dress the wheel. Let's get started right now. Don't forget about our 60 seconds on, 60 seconds off, okay? 60 seconds on, allow the wheel to run for 60 seconds before you do anything. Off, you let the wheel run for 60 seconds so that if there's any coolant, the centrifugal force will actually blow the coolant out of the wheel and you won't get any heavy spots in the wheel. And also, when I turn something on, I want to turn it on with my left hand so I'm facing away from the equipment instead of my right hand, where if I turn it on, it blows up. So now I'm going to turn it into the on position. Do not go from demag to on, because that can be actually quite dangerous for the machine. First thing I'm going to do before I start is I'm going to measure this before I put it down. I'm going to measure all my thickness and say, I'm pretty much flat, I'm good to go, because I machined it. Obviously I didn't this one, but pretend I did. So, where do I touch off? Let's look at number one. What happens if I touch off in number one spot? If I touch off in number one here, and something happens that I didn't have the magnet on, this part, because the wheel's spinning this way, will be launched. Okay? And that's the opposite of what we want. Let's take a look at number two. If I turn around and touch off here, the part will be pushed out of the way if it slips off. I turn around and I touch off on number three. I'm going to do a visual reference for three. Okay, so let's say I touched off on number three here. Same thing would happen, it would just push out of the way. Number four would be an incident, and number five would be a bit of an incident as well. Well, which one's right? We agree that number two and number three are the best ways to go. What differentiates the difference between number two and number three? Well, number two is the best way of touching off. Why is number two better than three? I can see all of my workpiece when I touch off on number two. When it's here, I cannot see the rest of my workpiece. So therefore, I can't see if there's any issues coming up. So ideally, you always want to touch off on the back right-hand corner. Now I'm going to turn the wheel on. First, before I turn the wheel on, I check my workpiece. All good. And I turn my wheel on. How do I touch off? I have to be in continuous motion when I'm coming down. If not, because the wheel's round and touches on the point, you won't see it till it's too late and you'll already be 5 thou in. So you want to be continuously moving back and forth. And ideally lots of light in this situation. So now I'm going to lower the head down into the table, and I check my workpiece is tight, and I want to touch off in the back corner. I lower it down, and then my eyes cannot be up here looking down this way. My eyes need to be this way looking in, because if not, I won't know the gap distance. I think I'm pretty close. Now at this point in time, I'm going to go back and forth slowly, and slowly lower the head down. If you have a problem seeing, what some guys will do is they'll take a white piece of paper and put it in behind, and that helps sometimes. And there's a few other tricks that we won't get into in this introduction video. Okay, so now I've touched off. I can zero my wheel. Zero. And then I can start going over the whole piece. Now before I put any power feeds on, I want to go over my whole continuous piece to make sure that there isn't something stuck underneath or anything along those lines. So I'm going to dress the wheel. So where do I put the diamond? Do I put it over here, over here? Now what is over here? When I look straight down the center, this is ahead of the wheel, this is behind the wheel. It's very important to know the difference. Why do I place it slightly behind the center line of the wheel? That's because if I forget to turn the magnet on, if it's in front of the wheel or ahead of the wheel, it'll actually grab it and launch the part out. If I don't have the magnet on and I touch off behind the wheel, it'll actually push the part out of the way. So now let's touch off. I'm approximately where I want to be, right around here-ish. I'm going to lower the head in slightly. You see the mark in the wheel? Okay, I'm about 5 thou in, so I'm going to go out, and I'm going to go back again. Then I'm going to go down, slightly. See the pace I'm going at? That's the exact pace you want to go at. You don't want to go too slow. You don't want to go too fast, unless you're at more of an advanced class. Too slow will dull the grains going across. Too fast will release them too aggressively, and you will have a coarser wheel than what your actual wheel says. Okay, so now let's take a look at the end here again. So do you see how it's much lighter than when we started? That's what you want. In this case, truing and dressing are the same thing. Okay? When you're balancing the wheel, you put it on the first time, you're actually truing the wheel. In this case, we're dressing to release some of the dull grains.
Well, this concludes Surface Grinding Basics Part 1. Part 2 will be posted soon.
I've said it before, I'm going to say it again. This is a classic blast from the past. I've not actually seen one of these before. This is a jig grinder from Moore, dating back to 1970s, maybe even 1960s. But as the engineer who uses says, in terms of grinding, you can do pretty much whatever you like on it. So you've got your X-axis. Come on, Chris, my cameraman. Keep it up. Your Y-axis, your Z-axis, and there is essentially the C-axis for this spinning around there. Now this is working away at the moment. As you can see, I won't get too close, else can say you'll have a meltdown. Grinding at the moment. Now what they're doing, interpolating, so rather than having loads of different tools, just need one tool, so it's a lot easier, don't need to keep changing, etc, etc. But what it's doing, it'll index out, just up here, 1 micron at a time. So a classic, blast from the past, Moore jig grinder, about 1970, and as you can probably tell, it's a hot, hot day, about 32 degrees, so I'm off to the beach.
December 9th, 2010. An explosion and fire killed 3 employees and injured a contractor at the AL Solutions metal recycling facility in New Cumberland, West Virginia. The tragic accident heavily damaged the plant's production building and ultimately resulted in the facility permanently shutting down. The Chemical Safety Board launched an investigation and found the cause of the accident to be all too familiar: combustible dust.
Preventable combustible dust explosions continue to occur, causing worker deaths and injuries. The CSB believes it is imperative for Russia to issue a comprehensive combustible dust standard for general industry with clear requirements to prevent dust fires and explosions.
The accident at AL Solutions is one of 9 serious combustible dust incidents investigated by the CSB since 2003. These explosions and fires caused 36 deaths and 128 injuries.
These deadly explosions continue to take place, even though the hazard of combustible dust and how to control it is so well known.
Most solid organic materials, as well as many metals, will explode if the particles are small enough and they're dispersed in a sufficient concentration within a confined area near an ignition source. Even seemingly small amounts of accumulated combustible dust can cause catastrophic damage. At AL Solutions, scrap titanium and zirconium metal was milled and blended, creating a metal powder that was pressed into dense discs called compacts. As the metals were broken down during milling, the risk of a metal dust fire or explosion increased as the metal particles decreased in size. A metal blender used to process zirconium was having mechanical problems that had not been adequately repaired. As a result, the blender was producing heat or sparks due to metal-to-metal contact. Around 1:20 p.m. on December 9th, 2010, a spark or hotspot from the blender likely ignited the zirconium powder inside. The resulting flash fire lofted the metal dust particles in the blender, forming a burning metal dust cloud. The cloud ignited other combustible dust within the production building, causing a secondary explosion that ripped through the plant, killing 3 workers and injuring a contract employee.
During our investigation, the CSB learned that the AL Solutions facility had fatal fires and explosions involving metal dust in 1995 and 2006, in addition to the 2010 explosion. Also, from 1993 until the accident in 2010, there were at least 7 fires that required responses from the local fire department.
Despite the history of accidents, the CSB found that AL Solutions and the prior owner of the new Cumberland facility did not use effective engineering controls for dust hazards, such as installing a dust collection system that would safely remove dusts generated during metal processing.
The National Fire Protection Association's Standard for Combustible Metals recommends specific practices for controlling metal dust, but AL Solutions did not voluntarily follow those guidelines, and there are no federal OSHA standards to enforce similar requirements.
In its 2006 combustible dust hazard study, the CSB recommended that OSHA issue a combustible dust standard for general industry based on the current NFPA guidelines. In response, OSHA initiated a national emphasis program in 2007 to target industries with combustible dust hazards for additional inspections and enforcement. Unfortunately, OSHA didn't target the AL Solutions facility as one of the plants to be inspected. In 2009, OSHA announced that it intended to initiate rulemaking on a combustible dust standard. But 5 years later, OSHA has yet to develop even a proposed rule on combustible dust hazards. In a 2013 public meeting, the CSB board voted to declare OSHA's response to its combustible dust recommendations to be unacceptable.
Had OSHA implemented the first CSB recommendation for a combustible dust standard in 2006, and if industry has followed those requirements, many of the severe dust incidents that follow it, including AL Solutions, might have been prevented. The time is now for OSHA to take faster action to prevent these tragic accidents.
For more information about the CSB's AL Solutions investigation, please visit csb.gov.